this short video, we're going to look at a number of examples that involve electrophilic addition to alkenes, but those in particular that involve rearrangements. In this first example, you can see that we have an alkene and it's an addition of HCl, so it's a hydrohalogenation. The things that we're going to say here also apply to other electrophilic addition reactions that involve a carbocation intermediate. Now you'll notice in this first example, I haven't shown you any products because I believe this is a simple enough example that you should be able to pick out that indeed we would expect to have a rearrangement. So let us proceed. You may remember that the first step, of course, is the attack of the pi bonds on our delta positive hydrogen. The intermediate will involve a carbocation. So it'll look something like this. And of course, we will expect to have, in a sense, a Markovnikov addition. In other words, the carbocation that will form will be on the more substituted carbon. We also have our chloride hanging around. The next step normally is, of course, the attack of the chloride at the carbocation. But I'd like you to take note of this particular kind of situation. So you have this carbocation and it's sitting right beside a more substituted carbon. What's going to happen in this case is, and it's helpful to draw in this additional hydrogen, is that we will have a hydride shift. And so I'm going to indeed show you the hydride shift. Note that my tail of the arrow is starting from the sigma bond, the bond between the carbon and the hydrogen. As a result of this hydride shift, we will end up having a carbocation sitting here, in other words, a tertiary carbocation. Now, while I'm showing you these as steps, in a sense, they occur spontaneously, immediately. There really isn't the intermediate that has only the secondary, or at least it would not exist for any substantial amount of time. But hopefully you can see why such a hydride shift will occur, because we have a secondary intermediate with the initial drawing, and then we move to a tertiary intermediate with the last drawing. As you might expect then, the next step is the chloride will attack at the carbocation, and our product would look something like the following. Now I'm not showing any stereochemistry in this case, but in fact it's not really important because the carbon that involves the addition of the chlorine is not chiral, and therefore we would not expect to have any enantiomers or diastereomers or any racemic mixtures. So in this particular example, I'd expect that you'd realize that the chlorine does not add at the carbon that I've just indicated with an asterisk, but rather it adds at this particular carbon right here. And this is because we expect a hydride shift to occur. So that's our first example. Let's proceed to look at another example. In this next example, while I actually think that you should be able to anticipate the product, I think for the most part you'll see this question where I've already drawn in the product and I'm asking you to explain it. So let's do that. So I'm going to draw in the expected product here, or at least what we'd expect to be the major product. And I'd like you to draw a mechanism to show how we would get there. So you may want to stop the video and just see if you can arrive at the correct answer. Now that you may have attempted this, let's do it together. It doesn't matter whether or not you start with the pi bond on the left-hand side or the pi bond on the right-hand side. Essentially, you'll arrive at the same product. So I started arbitrarily with the pi bond on the right-hand side. The attack on the hydrogen, the breaking of the hydrogen-chlorine bond. We will, of course, initially start with a carbocation on the more substituted carbon. So there's my carbocation. And I'm imagining, well, how can I get to that product? And it should be pretty clear to you that once again we're talking about a hydride shift. So the hydride shift would look something like this. And so now, of course, we end up with a carbocation just next door. And then naturally all that happens at this stage is that the chlorine that formed in our first step will attack at this carbocation And we'll end up with, of course, this particular product. Now this product does result in a carbon that is chiral. Note, of course, there's also a hydrogen. And so I can draw one of the products such that the chlorine is coming out at us and another product with the chlorine going away. And so the other possible product would be the following. So now the chlorine is going away, and for no other reason that we'd expect the attack to occur equally on both the top and the bottom of the carbocation, I'd expect these to be involved in a racemic mixture, that is a 50-50 mixture. Now one of the things, though, that we haven't explained in showing this is why would we have this hydride shift? Because we're going, of course, from a secondary carbocation to another secondary carbocation. But I would expect actually this secondary carbocation would be more stable. And that's because this is an example of an allelic carbocation. So in fact, this carbocation is stabilized by resonance. And as it turns out, that's even more important than stabilization by hyperconjugation. And so we would expect, for instance, this pi bond to move over, and I use that term loosely, and we could have a positive charge on the end here. One way or another, we have stabilization of this positive charge. That's only true when the carbocation is sitting in this particular structure such that we have an allelic carbocation. Note that it is possible actually for the chloride to in fact attack at that particular carbocation on the edge. Even though this is a primary carbocation, it is somewhat stabilized. So another possibility is I could have asked you, how is it possible for a chlorine to end up on the end carbon? And that's, again, because of this resonance structure. Okay, so we've looked at two examples that involve rearrangements. Let's look at a third example. This is a very common sort of example where we start with a ring structure, and adjacent to the ring structure we have a pi bond. Now I'm going to draw an anticipated major product. So most often the question would be asked like this, where I ask you to draw a mechanism that's consistent with forming this particular major product. Again, you may want to stop the video and give it a try yourself and then join us. Okay, so you might have tried this reaction yourself. Now let's do it together. They always start off in the same way, and so I hope that you actually are not afraid to explore, and that of course, okay, there's going to be this attack of the pi bond at the delta positive hydrogen, and we will end up forming the carbocation on the more substituted carbon. Okay, so we'll have something like this, and on the more substituted carbon. So now we have to figure out how we can move from this particular intermediate such that the positive charge will actually be on apparently a different carbon and involve a 5-membered ring instead of a 4-membered ring. One of the things that I find helpful in these sorts of problems is to actually number the carbons. And I'm not numbering for the purpose of naming, but just to keep track of all the carbons. So I'm going to go 1, 2, 3, 4, 5, 6, 7. So I have 7 carbons to work with, and I have to make sure that I don't lose any of those carbons. Now if I number the carbons over here, 1, 2, 3, 4, 5, 6, 7, perhaps you get a sense of how things have changed. Carbons 1 and 2 are the same, but it appears that somehow now in our final structure, carbon number 7 is bound to carbon number 3. And so indeed, what's going to happen next is not a hydride shift, but an alkyl shift, which will open up the ring. And so essentially what's going to happen is the bond between carbon 7 and 4, that sigma bond, is going to shift. And as a result, it'll open up the ring. Okay, now in opening up the ring, it doesn't matter exactly how you draw this ring, and in fact I would just go ahead and draw it and make sure that then you number your carbons. And so I'm anticipating a 5-membered ring as a result of this thing opening up. And so I'm going to still draw my other carbons here. So I'm going to have carbons 1, 2, 3, okay? And then I've got 4, 5, 6, and 7. So that's the outcome of this alkyl shift. One of the things to keep in mind, though, is that the positive charge has shifted. Carbon number 4 in our intermediate right here is making a full set of bonds. What's not shown is the bond to hydrogen. It doesn't have any formal charge. Whereas carbon number 4 in this particular case is still making a bond to a hydrogen, but it's no longer making that bond to carbon number 7. It's carbon number 4 that has the positive charge. Okay, so the positive charge has shifted as a result of this alkyl shift. Now this still doesn't explain how we get to our product with the chlorine on carbon number 3. Now you can see that currently this intermediate has a secondary carbocation, whereas the result of the attack on carbon number 3 would have been on a tertiary carbocation. So you might imagine that what we're going to have here is a hydride shift. And the hydride shift will be such that we'll end up going from a secondary carbocation to a tertiary carbocation. Now I just drew in a hydrogen on carbon number 4, but note there's also a hydrogen on carbon number 3. So I want you to stop for a minute and think, all right, which hydrogen is going to be moving here? Okay, so hopefully you guessed that it was the hydrogen on carbon number 3. And so we're going to have this hydride shift. So once again, I'm going to draw in this ring. I don't really need to draw the hydrogen on carbon number 4. But I do know that now there's a positive charge on carbon number 3. I will number my carbons just to keep things straight here. So essentially, now we're at the end of our mechanism in that the chloride that would have formed in the very first step is now going to attack at carbon number 3 and result in forming this product. Now in this particular case, that carbon number 3 is in fact not chiral. There's a plane of symmetry that runs through our cyclopentane ring. And therefore I don't need to worry about any particular stereochemistry. So I would draw the mechanism just to show how we can begin with a 4-membered ring and end up with a 5-membered ring and also do this electrophilic addition. So that's our third example. In the fourth example, you can see that I have already drawn the product. And once again, I encourage you to stop the video and give it a try yourself. Okay, so perhaps you have tried. And again, this first step is always going to be this first step. And so at least I'm hoping that you did that. Now in this case, it doesn't matter where we put the positive charge. Given where I'm aiming for the product though, I'm going to put my positive charge here. I know that therefore the other carbon would have picked up the hydrogen. Of course, if the chloride that formed now attacked at that positive charge, I still would not get the desired product. As you might imagine, there is once again a hydride shift. Okay, so let's draw the hydride shift. So got that oxygen there. Now the positive charge is on the desired carbon. I can actually just go ahead and draw in the chloride that would have formed in the first step and show the attack. And that would result in our product. Note that this carbon is indeed chiral, and there would be an attack both from the top and the bottom, and you'd end up with a racemic mixture. You will notice that our first intermediate has a carbocation that's a secondary carbocation. The second intermediate also involves a secondary carbocation. So once again, you might wonder, what is the advantage? Why this hydride shift? Well, we have mentioned in class this important phenomenon. And at first it might seem counterintuitive that you've got this electronegative oxygen right adjacent to the positive charge. But this is the perfect example of having a lone pair next to a positive charge and the possibility of having resonance. And in fact, your book recommends that you draw this resonance form, which is actually the more stable resonance form, and this is therefore showing that it's stabilizing the carbocation, and that in fact the chloride will attack this more stable resonance form, resulting in our product. Now, this last intermediate that I've drawn, the last resonance form, is considered to be more stable because all atoms have an octet. I'm going to try to encourage you to remember this particular situation, as this is one of the more powerful forms of stabilization of a positive charge, as is the case that we just finished looking at on the previous page, where we have stabilization by resonance. So this example number 2 and this example number 4, both involving stabilization by resonance. These are powerful ways by which the positive charge can be stabilized, more powerful than simply stabilization by hyperconjugation. So these are 4 examples of when you would expect to find rearrangements. In many examples, I already give you an anticipated product, and you need to work your way through. If the nucleophile, that is in this case the halide, the chloride, if the nucleophile is on a carbon that was not originally involved in the pi bond, you should anticipate that there would be rearrangements. Hopefully you found this video to be helpful in exploring rearrangements in electrophilic addition reactions.